In the depths of space, 1,400 light years from Earth, something impossible is happening. A star is behaving in ways that shouldn't exist, according to everything we know about stellar physics. Tonight, let yourself sink into this mystery. Forget about time, forget about tomorrow's obligations. Allow your mind to drift as we explore one of the most perplexing objects ever discovered in our universe. This isn't a story with easy answers. It's a journey through the very limits of human understanding, where our most brilliant scientists found themselves grasping for explanations that seemed to belong more in science fiction than in peer-reviewed journals. So settle in, breathe deeply, and let this cosmic puzzle unfold at its own pace. What we're about to examine challenges not just our understanding of stars, but our assumptions about what's possible in the universe itself. The year was 2009, and the Kepler Space Telescope had just begun its revolutionary mission to find planets orbiting distant stars. The concept was elegantly simple. Point the telescope at a patch of sky containing over 150,000 stars and watch for the telltale dimming that occurs when a planet passes in front of its host star. These transit events, as astronomers call them, create distinctive signatures in the light curves that Kepler recorded with unprecedented precision. For most stars, the data was exactly what scientists expected. A planet would cause a brief, shallow dip in brightness, typically lasting a few hours to a few days, with the dimming rarely exceeding 1 or 2%. The pattern would repeat with clockwork regularity as the planet completed its orbit. Thousands of these planetary transits were detected, each one adding to our growing catalog of worlds beyond our solar system. But among these 150,000 stars, one stood out as fundamentally different. Designated KIC 8462852 in the Kepler catalog, this particular star would later earn the nickname Tabby's star, after astronomer Tabitha Boyajian, who led much of the groundbreaking research into its bizarre behavior. What made this star so unusual wasn't what it did occasionally, but what it did consistently, defying every model and theory that astronomers had developed over centuries of stellar observation. The first hint that something was amiss came from the automated algorithms designed to flag potential planet candidates. These sophisticated programs were trained to recognize the smooth, predictable dips caused by planetary transits, but when they analyzed the data from KIC 8462852, they found patterns that made no sense whatsoever. The star wasn't just dimming by the 1 or 2% expected from a planetary transit. It was dimming by staggering amounts, sometimes as much as 22% of its total brightness. To put this in perspective, imagine if our sun suddenly dimmed by more than a fifth of its normal brightness. The effect would be immediately noticeable on Earth, causing significant climatic changes and ecological disruption. For a star to dim by such an enormous amount suggested that something truly massive was blocking its light, something far larger than any known planet. But the strangeness didn't end there. These dramatic dimming events weren't following any predictable pattern. They occurred at irregular intervals, lasted for varying amounts of time, and showed completely asymmetric shapes in the light curves. Some dips were sharp and angular, others were broad and gradual. Some showed multiple peaks and valleys, as if whatever was causing the dimming had an incredibly complex, irregular structure. The initial reaction from the astronomical community was skepticism tinged with excitement. Skepticism because the data seemed to violate basic principles of planetary formation and orbital mechanics. Excitement because if the observations were real, they represented something entirely unprecedented in the study of stellar systems. Tabitha Boyajian, then a postdoctoral researcher at Yale University, became fascinated by this anomalous star. She began what would become years of intensive analysis, diving deep into the Kepler data to understand what could possibly be causing such bizarre behavior. What she found only deepened the mystery. The star itself appeared completely normal in every other respect. It was an F-type star, somewhat larger and hotter than our Sun, with a surface temperature of around 6,750 Kelvin. Its spectral characteristics showed no unusual features. It wasn't a variable star, meaning its intrinsic brightness remained steady. The dimming events were clearly caused by something external to the star itself, something passing in front of it and blocking the light. But what could cause such dramatic, irregular dimming? The first and most obvious candidate was a swarm of comets. Perhaps the star had captured a large group of comets from interstellar space, or maybe its gravitational influence had disturbed a distant comet cloud, sending thousands of icy bodies on chaotic orbits through the inner system. When these comets approached the star, they would sublimate, creating vast clouds of gas and dust that could block significant amounts of starlight. The comet hypothesis had several attractive features. It could explain the irregular timing of the dimming events, since comets follow elliptical orbits that would bring them close to the star at unpredictable intervals. It could also account for the varying depths and durations of the dips, depending on the size and density of the comet swarm passing in front of the star at any given time. However, the more Boyajian and her colleagues examined this possibility, the more problems they encountered. The amount of material required to block 22% of a star's light was truly staggering. Even accounting for the efficiency of fine dust particles at scattering light, the comet swarm would need to contain an enormous amount of material, perhaps equivalent to hundreds of Earth masses worth of comets. Moreover, the timescales involved didn't quite match what would be expected from comets. The longest dimming events lasted for days or even weeks, suggesting that whatever was causing the blockage was either moving very slowly or was incredibly extended in space. A typical comet, even with a substantial tail, would transit a star much more quickly. As word of the discovery spread through the astronomical community, other researchers began proposing alternative explanations. Perhaps the star was surrounded by a young, still-forming planetary system with massive clouds of dust and debris left over from the planet formation process. This circumstellar disk could have clumpy, irregular structure that would create the observed dimming patterns as different regions passed in front of the star, but this explanation also had significant problems. KIC 8462852 showed no excess infrared emission, which would be expected if it were surrounded by large amounts of warm dust. Young stellar systems with massive debris disks typically glow brightly in infrared wavelengths as the dust absorbs starlight and re-emits it as heat. The complete absence of this infrared signature suggested that whatever was causing the dimming wasn't a conventional dust disk. Another possibility was that the star had recently experienced some kind of catastrophic collision between large planetary bodies. If two Mars-sized planets had smashed into each other in the relatively recent past, they could have created an enormous cloud of debris that was still orbiting the star. This debris could have complex, chaotic structure that would explain the irregular dimming patterns. The collision hypothesis was intriguing because it could potentially explain both the dramatic dimming and the lack of infrared excess. If the collision had occurred within the last few thousand years, the debris might still be cool enough not to emit significant infrared radiation, while still being substantial enough to block large amounts of visible light. However, calculating the probability of observing such a recent collision raised uncomfortable questions. Planetary collisions of this magnitude would be extremely rare events, occurring perhaps once every few million years in a typical stellar system. The odds of happening to observe one of the very few stars in our galaxy currently experiencing the aftermath of such a collision seemed vanishingly small. As researchers continued to grapple with these conventional explanations, each seeming to have fatal flaws or require improbable coincidences, some began to consider more exotic possibilities. The data was so unusual, so far outside the bounds of normal stellar behavior, that it seemed to demand equally unusual explanations. One of the most intriguing aspects of the dimming patterns was their apparent complexity and structure. When astronomers looked closely at the shape of the light curves during dimming events, they found features that seemed almost engineered. There were sharp transitions, multiple peaks and valleys, and asymmetric profiles that suggested the blocking material had a highly organized, non-random structure. This observation led some researchers to consider the possibility that the dimming might be caused by artificial structures rather than natural phenomena. If an advanced technological civilization had built massive constructions around the star, these megastructures could potentially explain the observed light curves. The concept of stellar megastructures wasn't entirely new to science. In 1960, physicist Freeman Dyson had proposed that a sufficiently advanced civilization might eventually construct a sphere or swarm of structures around their star to capture all of its energy output. Such a Dyson sphere would be the ultimate expression of a civilization's technological prowess, allowing them to harness the full power of their star for their energy needs. While a complete Dyson sphere would render the star completely invisible, a partially constructed one, or a Dyson swarm made up of many individual components could create exactly the kind of irregular dimming patterns observed around KIC 8462852. Different components of the megastructure passing in front of the star would block different amounts of light, creating the complex asymmetric dips in brightness that defied conventional astronomical explanation. The megastructure hypothesis was simultaneously the most exciting and most problematic explanation for the star's behavior. On one hand, it offered a potential solution to all the puzzling aspects of the observations. It could explain the enormous depth of the dimming events, their irregular timing, their complex shapes, and the absence of infrared excess. An artificial structure made of solid materials wouldn't necessarily emit significant amounts of heat, unlike a natural dust cloud. On the other hand, the implications of this explanation were staggering. If confirmed, it would represent the first detection of an advanced alien civilization, fundamentally changing our understanding of our place in the universe. The structures would need to be truly massive, perhaps millions of kilometers across, representing an engineering project on a scale that challenged human imagination. The scientific community approached this possibility with appropriate caution. Extraordinary claims require extraordinary evidence, and the detection of alien technology would certainly qualify as an extraordinary claim. Before seriously considering the megastructure hypothesis, astronomers needed to exhaust all possible natural explanations and gather additional evidence to support or refute the artificial interpretation. This cautious approach led to an intensive observational campaign to study KIC 8462852 in greater detail. Telescopes around the world began monitoring the star continuously, hoping to catch it in the act of dimming and gather more detailed data about the nature of whatever was blocking its light. One of the first major breakthroughs came from examining the star's long-term brightness history. Researchers dug through archival observations dating back over a century, looking for any signs of unusual behavior in the past. What they found was deeply unsettling. The star appeared to be getting dimmer over time, and not just during the dramatic dimming events that Kepler had detected. Analysis of photographic plates from the early 20th century showed that KIC 8462852 had faded by approximately 20% over the course of a century. This gradual, long-term dimming was completely unprecedented among normal stars and added another layer of mystery to an already baffling object. The century-long dimming trend seemed to rule out many of the proposed explanations. A swarm of comets or collision debris would be expected to disperse over time, not maintain a steady blocking effect for decades. Even a partially constructed megastructure would presumably show some evolution in its light-blocking properties as construction progressed. Some researchers suggested that the long-term dimming might be caused by a gradual increase in the amount of dust or debris around the star. Perhaps KIC 8462852 was slowly accreting material from interstellar space, building up clouds of particles that incrementally reduced the amount of light reaching Earth. However, the timescales involved seemed too short for this process, and the lack of infrared emission remained a significant problem. As more data accumulated, astronomers began to notice additional peculiarities in the star's behavior. The dimming events showed a preference for certain wavelengths of light, with blue light being more strongly affected than red light. This wavelength dependence provided important clues about the size and nature of the particles responsible for the dimming. When light encounters small particles, it scatters according to well-understood physical principles. Very small particles, much smaller than the wavelength of visible light, scatter blue light more efficiently than red light. This is why Earth's sky appears blue and why sunsets look red. Larger particles, comparable to or larger than the wavelength of light, tend to block all colors more equally. The wavelength dependence observed in KIC 8462852's dimming events suggested that the blocking material consisted of very small particles, perhaps only nanometers to micrometers in size. This finding was consistent with fine dust, either from comets, collision debris, or possibly even artificial materials. However, it didn't definitively distinguish between natural and artificial origins. The search for additional clues led astronomers to examine the star's radio emissions, looking for any signs of technological activity. Radio telescopes around the world pointed toward KIC 8462852, scanning across a wide range of frequencies for any signals that might indicate the presence of an advanced civilization. These radio observations yielded no clear detections of artificial signals, but they weren't sensitive enough to rule out all forms of technological activity. A civilization capable of building megastructures might use communication technologies that were either too weak to detect at interstellar distances or operated on frequencies outside the range of terrestrial radio telescopes. The lack of obvious radio signals didn't eliminate the megastructure hypothesis, but it did reduce its probability somewhat. Most theoretical models of advanced civilizations suggested that such beings would generate detectable electromagnetic emissions as a byproduct of their activities. The absence of such signals, while not conclusive, added weight to the argument for natural explanations. Meanwhile, additional Kepler data became available as the mission continued, providing more examples of the star's unusual dimming behavior. Each new observation added to the growing database of light curves, allowing astronomers to study the phenomenon in greater statistical detail. One particularly intriguing discovery was that the dimming events seemed to show some evidence of periodicity, though not the simple regular periods expected from planetary transits. Instead, there appeared to be multiple overlapping cycles, as if several different processes or objects were simultaneously affecting the star's brightness. This multi-periodic behavior added another layer of complexity to an already convoluted puzzle. The apparent periodicity offered some hope for predictive modeling. If astronomers could identify the underlying cycles, they might be able to predict when future dimming events would occur, allowing for coordinated observational campaigns to study them in real time. However, the periods were sufficiently complex and uncertain that definitive predictions remained elusive. As the scientific investigation continued, KIC 8462852 began to attract attention from beyond the astronomical community. Science journalists picked up the story, and the possibility of alien megastructures captured the public imagination in a way that few astronomical discoveries had before. The star acquired its popular nickname, Tabby's Star, and became the subject of countless articles, blog posts, and online discussions. This public attention brought both benefits and challenges to the research effort. On the positive side, it generated funding and support for additional observations, allowing astronomers to dedicate more telescope time and resources to studying the star. Citizen scientists also began contributing to the effort, analyzing data and proposing new hypotheses for the strange behavior. However, the media attention also created pressure to reach definitive conclusions quickly, even when the data remained ambiguous. The scientific process of careful hypothesis testing and peer review sometimes conflicted with the public's desire for immediate answers to the mystery of whether we had found evidence of alien technology. As 2015 progressed, Boyajian and her colleagues continued their detailed analysis of the Kepler data, looking for any patterns or features that might provide definitive clues about the nature of the dimming events. They developed sophisticated computer models to test various scenarios, from comet swarms to debris clouds to artificial structures. One of the most detailed analyses focused on the largest dimming event in the Kepler data, a dramatic fade that reduced the star's brightness by over 20% and lasted for several days. The shape of this particular light curve was extraordinarily complex, showing multiple peaks and valleys that seemed to suggest a highly structured blocking object. Computer simulations of various natural phenomena struggled to reproduce the exact shape of this dimming event. Swarms of randomly distributed comets or debris particles typically produced smoother, less structured light curves. To match the observations required either very specific, unlikely configurations of natural materials or objects with artificial regularity and organization. The difficulty in explaining the observations with conventional models led some researchers to propose hybrid scenarios. Perhaps KIC 8462852 was indeed surrounded by natural debris, but this material had been organized or concentrated by some unusual process. For example, the gravitational influence of unseen planets might have shepherded comet fragments into specific orbital configurations that created the observed dimming patterns. These gravitational shepherding scenarios offered a middle ground between purely natural and artificial explanations. They didn't require the existence of alien technology, but they did invoke relatively exotic planetary dynamics that would be unusual even by the standards of our rapidly expanding knowledge of exoplanetary systems. Throughout this period of intense analysis and speculation, one fundamental challenge remained: the sheer rarity of the phenomenon. Despite Kepler's observation of over 150,000 stars, KIC 8462852 appeared to be completely unique. No other star in the entire Kepler catalog showed similar behavior, which raised profound questions about the nature and origin of whatever was causing the dimming. The uniqueness of the phenomenon made it difficult to develop general theories or test hypotheses through comparison with similar objects. In most areas of astronomy, discoveries are eventually understood by studying multiple examples of the same type of object. Pulsars, for instance, were initially mysterious until astronomers found enough of them to recognize the underlying patterns and develop theoretical models. KIC 8462852's apparent uniqueness suggested either that the underlying cause was extremely rare in the galaxy, or that the observations were somehow influenced by a very specific set of circumstances that made this particular star visible, while similar objects remained hidden. Neither possibility was particularly comforting for researchers trying to understand the phenomenon. The rarity problem led some astronomers to question whether the observations might be affected by instrumental artifacts or data processing errors. The Kepler telescope was a remarkable instrument, but like all complex systems, it was subject to various technical issues that could potentially create false signals in the data. Extensive analysis of the Kepler data processing pipeline revealed no obvious sources of systematic error that could explain the dimming events. The signals appeared to be real astrophysical phenomena, not artifacts of the observational process. However, the possibility of subtle, unrecognized instrumental effects couldn't be completely ruled out without independent confirmation from other telescopes. This need for independent verification drove efforts to observe KIC 8462852 with ground-based telescopes and other space-based instruments. While these observations couldn't replicate the years-long, continuous monitoring that Kepler had provided, they could potentially detect new dimming events and confirm that the phenomenon was genuine. The ground-based observational campaigns faced significant challenges. KIC 8462852 was relatively faint as seen from Earth, requiring large telescopes and careful photometric techniques to detect small changes in brightness. Moreover, the irregular timing of the dimming events meant that most observations would show the star in its normal, undimmed state. Despite these challenges, several research groups began systematic monitoring programs hoping to catch the star during one of its dramatic fading episodes. These efforts required patience and persistence, as there was no way to predict when the next major dimming event might occur. In addition to photometric monitoring, astronomers began studying KIC 8462852 with spectroscopic techniques, analyzing the detailed characteristics of its light to look for clues about the blocking material. Spectroscopy could potentially distinguish between dust particles of different compositions and sizes, providing important information about the nature of whatever was causing the dimming. The spectroscopic observations revealed that KIC 8462852 was indeed a normal F-type star with no unusual features in its spectrum. The star's surface composition, temperature, and other properties all appeared typical for its stellar class. This finding reinforced the conclusion that the dimming was caused by external material rather than intrinsic changes in the star itself. However, spectroscopy during dimming events proved more challenging. The reduced brightness of the star during these episodes made it difficult to obtain high-quality spectra with sufficient signal-to-noise ratio to detect subtle features. Most ground-based telescopes simply weren't sensitive enough to perform detailed spectroscopic analysis of the star when it was significantly dimmed. As 2016 approached, the mystery of KIC 8462852 remained unsolved despite nearly 2 years of intensive study. The accumulated evidence pointed to some form of external material blocking the star's light, but the exact nature of this material continued to elude definitive identification. Each proposed explanation had serious problems, and the truly exotic nature of the observations kept the possibility of artificial origins alive in scientific discussions. The persistence of the mystery began to drive technological innovation in astronomical observation. New instruments and analysis techniques were developed specifically to study objects like KIC 8462852, pushing the boundaries of what was possible with current technology. The star became a test case for advanced photometric methods and data analysis algorithms. One particularly promising development was the application of machine learning techniques to the analysis of stellar light curves. Computer algorithms trained on large datasets of stellar observations could potentially identify subtle patterns and correlations that human analysts might miss. These approaches offered new ways to extract information from the complex, irregular dimming patterns that characterized KIC 8462852. The machine learning analysis revealed some intriguing statistical properties of the dimming events, including correlations between the depth, duration, and shape of different episodes. These correlations suggested that whatever was causing the dimming had consistent physical properties, even though its behavior appeared chaotic and unpredictable. The statistical analysis also provided new constraints on proposed explanations. For example, purely random distributions of debris or comet fragments would be unlikely to produce the observed correlations between different dimming events. The data seemed to require either some organizing principle that controlled the behavior of natural materials, or alternatively, an artificial system with inherent design logic. As the scientific investigation continued, KIC 8462852 also began to influence broader discussions about the search for extraterrestrial intelligence. The star represented a new category of potentially detectable alien technology, different from the traditional focus on radio signals or other forms of electromagnetic communication. The concept of detecting alien civilizations through their astroengineering projects offered several advantages over conventional SETI approaches. megastructures would be visible across vast distances and wouldn't require the aliens to be actively trying to communicate with other civilizations. A Dyson sphere or similar construction would be detectable simply as a consequence of its existence, regardless of its builder's intentions regarding interstellar communication. This realization led to proposals for systematic surveys designed to find other stars showing similar anomalous behavior. If KIC 8462852 represented alien technology, there might be other examples waiting to be discovered in the vast databases of stellar observations accumulated by various astronomical surveys. The search for additional anomalous stars became a priority for several research groups. Automated algorithms were developed to scan through millions of stellar light curves, looking for objects with unusual dimming patterns or long-term brightness variations. These searches represented a new approach to SETI, focusing on the astronomical consequences of alien engineering rather than deliberate signals. The early results of these surveys were mixed. While several stars were identified with unusual variability, none showed the extreme complex behavior that made KIC 8462852 so remarkable. This could mean that the phenomenon was indeed extremely rare, whether natural or artificial, or that the search techniques needed further refinement to identify more subtle examples. As 2016 progressed, a new development began to change the trajectory of research into KIC 8462852. Citizen scientists and amateur astronomers, inspired by the publicity surrounding the star, began their own observational campaigns using smaller telescopes and sophisticated digital cameras. While these amateur observations couldn't match the precision of professional astronomical instruments, they offered something equally valuable: to monitor the star continuously over long periods. Professional telescopes typically had limited time available for any single object, but dedicated amateur astronomers could observe KIC 8462852 night after night, weather permitting. This citizen science approach proved remarkably effective. In May 2017, amateur observers detected the first significant dimming event since the end of the Kepler mission, providing the astronomical community with advance warning that allowed professional telescopes around the world to begin coordinated observations. The 2017 dimming event, dubbed ELSI by the research team, was observed by dozens of telescopes simultaneously, providing the most comprehensive dataset ever collected during one of the star's mysterious fading episodes. For the first time, astronomers had real-time spectroscopic and photometric data covering the entire duration of a dimming event. The results of these coordinated observations were both illuminating and puzzling. The dimming showed clear wavelength dependence, with blue light being more strongly affected than red light, confirming the presence of small dust particles. However, the specific characteristics of this wavelength dependence didn't match any simple dust models. More surprisingly, infrared observations during the dimming event detected a subtle but significant increase in the star's infrared brightness. This infrared excess suggested that the blocking material was indeed absorbing starlight and re-emitting it as heat, contradicting earlier observations that had found no infrared signature. The detection of infrared emission during dimming events was a crucial piece of evidence that helped narrow down the possible explanations. The presence of warm dust ruled out solid, metallic megastructures, which wouldn't be expected to emit significant amounts of infrared radiation. Instead, the observations pointed toward natural dust clouds, possibly created by comets or other small bodies. However, the dust interpretation faced its own challenges. The amount of infrared emission was much smaller than would be expected from a conventional dust cloud, dense enough to block 20% of a star's light. The dust appeared to be either unusually cold or present in much smaller quantities than the dimming suggested. These apparent contradictions led researchers to propose more sophisticated dust models. Perhaps the blocking material consisted of very fine particles that were efficient at scattering visible light, but poor at absorbing and re-emitting infrared radiation. Alternatively, the dust might be organized into thin, filamentary structures that could block large amounts of light while containing relatively little total material. The 2017 observations also provided important information about the three-dimensional structure of whatever was causing the dimming. By comparing the timing and depth of dimming as seen from different wavelengths, astronomers could infer details about the size, density, and spatial distribution of the blocking material. These structural analyses suggested that the dimming was caused by multiple, distinct clumps or streams of material, rather than a single uniform cloud. The material appeared to be organized on scales of millions of kilometers, with complex internal structure that created the irregular, multi-peaked dimming profiles observed in the light curves. The evidence for complex, large-scale structure in the blocking material was difficult to reconcile with simple comet models. While comet tails could certainly extend over millions of kilometers, maintaining coherent structure over such distances required specific conditions that weren't commonly observed in the solar system. Some researchers proposed that KIC846282 might be surrounded by a particularly massive and active comet cloud, perhaps stirred up by the gravitational influence of unseen planets or passing stars. This enhanced comet activity could create the observed complex structures while still remaining within the realm of natural phenomena. The planetary perturbation hypothesis gained support from theoretical modeling studies that showed how the gravitational influence of giant planets could organize comet debris into specific orbital configurations. Under the right circumstances, these configurations could create exactly the kind of irregular, complex dimming patterns observed around KIC 8462852. However, the planetary models required very specific assumptions about the number, masses, and orbits of the hypothetical planets. The scenarios that best matched the observations involved multiple giant planets in highly eccentric orbits, a configuration that would be unusual even by the diverse standards of known exoplanetary systems. As 2017 continued, additional dimming events were detected and observed by the growing network of professional and amateur telescopes monitoring the star. Each new event provided additional data points for testing various theoretical models and refining our understanding of the phenomenon. One particularly significant observation was the detection of very shallow dimming events, fades of only a few percent that had been below the detection threshold of earlier observations. These minor dimming episodes suggested that whatever was causing the major fading events was also responsible for continuous low-level variability in the star's brightness. The discovery of continuous variability had important implications for understanding the nature of the blocking material. It suggested that KIC 8462852 was surrounded by a persistent dynamic environment of dust or debris, rather than being occasionally visited by transient objects like individual comets. This persistent environment model led researchers to reconsider the collision hypothesis. Perhaps KIC 8462852 had indeed experienced a major collision between planetary bodies, but instead of a single recent event, the system might be experiencing ongoing collisional activity. A population of asteroids or planetesimals in chaotic orbits could create continuous dust production through frequent smaller collisions. The ongoing collision model had several attractive features. It could explain both the major dimming events and the continuous low-level variability. It could account for the complex structure observed in the blocking material, and it didn't require the extremely improbable coincidence of observing a single recent catastrophic collision. However, the ongoing collision model also faced significant challenges. Maintaining high levels of collisional activity over extended periods required a large population of objects in unstable orbits. The energy dissipation from frequent collisions would tend to damp out the chaotic orbital dynamics over relatively short timescales, making it difficult to sustain the process indefinitely. Moreover, the ongoing collision scenario would be expected to produce detectable amounts of warm dust that should be visible in infrared observations. While some infrared emission had been detected during dimming events, the overall infrared excess from KIC 8462-852 remained much lower than predicted by collision models. As 2018 approached, the accumulating observational evidence began to paint a clearer picture of KIC 8462-852, even though many fundamental questions remained unanswered. The star was definitely surrounded by material that occasionally blocked large amounts of its light. This material consisted of small dust particles organized into complex, large-scale structures. The dimming events showed both random and periodic components, suggesting multiple underlying processes. The weight of evidence increasingly favored natural explanations over artificial ones, though the exact nature of the natural process remained unclear. The detection of infrared emission during dimming events was particularly important in ruling out solid megastructures, though it didn't definitively eliminate all forms of alien technology. The scientific investigation of KIC 8462-852 had also driven significant advances in astronomical observation and analysis techniques. New methods for detecting and characterizing transient astronomical phenomena had been developed and tested. The collaboration between professional astronomers and citizen scientists had proven remarkably effective, creating new models for conducting large-scale observational campaigns. Perhaps most importantly, the study of KIC 8462-852 had demonstrated the value of pursuing anomalous observations, even when they seemed to challenge fundamental assumptions about how the universe works. While the star might not represent evidence of alien technology, it had revealed new phenomena and pushed the boundaries of our understanding of stellar systems. The broader impact of KIC 8462-852 extended beyond astronomy into the realm of astrobiology and the search for extraterrestrial intelligence. The star had shown that unusual astronomical observations could potentially provide evidence of alien civilizations, validating the concept of SETI through astroengineering detection. Even if KIC 8462-852 itself turned out to have a natural explanation, the investigation had established important methodological frameworks for identifying and studying potentially artificial astronomical phenomena. Future surveys would be better equipped to recognize and analyze similar anomalies, whether they proved to be natural or artificial in origin. The story of KIC 8462-852 also highlighted the importance of long-term astronomical monitoring. The star's unusual behavior had only been discovered through years of continuous observation by the Kepler mission. Many astronomical phenomena occur on timescales that require patient, systematic study over extended periods. This lesson influenced the design of future astronomical surveys and space missions. Projects like the Transiting Exoplanet Survey satellite and the upcoming Vera Rubin Observatory were specifically designed to provide long-term, systematic monitoring of large numbers of astronomical objects, potentially discovering additional examples of rare or unusual phenomena. As 2018 progressed, the observational campaign around KIC 8462-852 continued to yield new discoveries and insights. The star's behavior showed evidence of evolution over time, with the characteristics of dimming events changing in subtle but measurable ways. This temporal evolution provided additional constraints on theoretical models and helped researchers understand the underlying physical processes. One particularly intriguing development was the apparent correlation between the depth of dimming events and their duration. Deeper dimming episodes tended to last longer, suggesting that the blocking material had consistent physical properties even as it evolved over time. This correlation provided support for models involving coherent structures like dust streams or debris clouds. The temporal evolution of the dimming events also revealed seasonal patterns that might be related to the orbital dynamics of whatever was causing the phenomenon. These patterns were subtle and required careful statistical analysis to detect, but they provided important clues about the geometry and kinematics of the system. The seasonal patterns were particularly interesting because they suggested that Earth's orbital motion around the Sun might be influencing our view of the KIC 846285 system. This geometric effect could provide information about the three-dimensional structure of the blocking material and its orbital characteristics. By 2019, the scientific consensus around KIC 846285 had largely settled on natural explanations involving dust and debris, though significant uncertainties remained about the specific mechanisms responsible for creating and organizing this material. The alien megastructure hypothesis, while not completely eliminated, was considered much less likely than natural alternatives. The shift away from artificial explanations was driven primarily by the accumulating evidence for dust-like properties in the blocking material, the wavelength dependence of the dimming, the detection of infrared emission, and the statistical properties of the dimming events all pointed toward small particles rather than solid structures. However, the natural explanations still faced significant challenges in explaining all aspects of the observations. The sheer scale and complexity of the dimming events remained difficult to account for with conventional models of stellar systems. KIC 846285 continued to represent an extreme case that pushed the boundaries of what was considered normal astronomical behavior. This extreme nature led some researchers to propose that KIC 846285 might represent a rare but natural phenomenon that occurred during specific phases of stellar evolution. Perhaps the star was passing through a particularly dense region of interstellar dust, or maybe it was experiencing unusual activity related to its age and evolutionary state. The interstellar dust hypothesis suggested that KIC 846285 might be encountering clouds of material left over from ancient stellar explosions or other cosmic events. As the star moved through its local galactic environment, it could be sweeping up this material, creating the observed dimming effects. While the interstellar dust model could potentially explain some aspects of the observations, it faced the same problems as other dust-based explanations. The amount of material required to create the observed dimming was enormous, and the organized, structured nature of the dimming events was difficult to reconcile with random encounters with interstellar clouds. The stellar evolution hypothesis proposed that KIC 846285 might be undergoing some form of enhanced mass loss or unusual surface activity that was creating circumstellar dust. While F-type stars like KIC 846285 weren't typically known for such behavior, stellar evolution was a complex process that could potentially produce unexpected phenomena under specific circumstances. However, detailed spectroscopic studies of KIC 846285 showed no evidence of enhanced mass loss or unusual stellar activity. The star's spectrum remained remarkably normal and stable, showing none of the features typically associated with active or evolving stars. As the 2000s drew to a close, KIC 846285 had become one of the most studied individual stars in the galaxy, with hundreds of research papers published about its unusual properties. The mystery remained unsolved, but the investigation had yielded valuable insights into stellar systems, dust physics, and the methodology of astronomical research. The star had also become a cultural phenomenon, inspiring countless works of science fiction and capturing the public imagination in ways that few astronomical discoveries had achieved. The possibility, however remote, that KIC 846285 might represent evidence of alien technology continued to fascinate people around the world. This cultural impact reflected deeper human questions about our place in the universe and the possibility of intelligent life beyond Earth, KIC 8462852 had provided a tangible focus for these ancient philosophical questions, grounding them in concrete observational data and scientific methodology. The investigation of KIC 8462852 also demonstrated the evolution of astronomy in the 21st century. The discovery relied on space-based observations, automated data analysis, international collaboration, and citizen science participation. It represented a new model of astronomical research that leveraged technology and global connectivity to tackle complex problems. As the 2020s began, new observational capabilities became available that offered fresh opportunities to study KIC 8462852. The James Webb Space Telescope, with its unprecedented infrared sensitivity, promised to provide detailed information about the dust and debris around the star. Ground-based telescopes with adaptive optics could potentially resolve spatial structure in the circumstellar environment. These new observations would be crucial for finally solving the mystery of KIC 8462852. The infrared capabilities of modern telescopes could definitively characterize the dust properties and determine whether the blocking material matched any known natural phenomena. High-resolution imaging might reveal the spatial distribution and dynamics of the circumstellar material. The continued study of KIC 8462852 also benefited from the discovery of additional unusual stars with similar, though less extreme, properties. These related objects provided comparative data that helped researchers understand which aspects of KIC 8462852's behavior were unique and which represented more general phenomena. The growing sample of anomalous stars suggested that KIC 8462852 might not be as unique as initially thought. Instead, it might represent the extreme end of a spectrum of stellar variability that was only beginning to be recognized and understood. This possibility opened new avenues for research and offered hope for eventually developing comprehensive theoretical models. As observational techniques continued to improve and more data accumulated, the scientific community remained optimistic that the mystery of KIC 8,462,852 would eventually be solved. The star had already taught us valuable lessons about the diversity and complexity of the universe, regardless of whether its ultimate explanation proved to be mundane or extraordinary. The story of KIC 8462852 serves as a reminder that the universe continues to surprise us, even after centuries of astronomical observation and theoretical development. There are still phenomena waiting to be discovered that challenge our understanding and force us to reconsider our assumptions about how the cosmos works. In the end, whether KIC 8462852 represents advanced alien technology, an unusual natural phenomenon, or something entirely unexpected, its discovery and investigation exemplify the best aspects of scientific inquiry. The star has driven technological innovation, international collaboration, and careful hypothesis testing, while maintaining the sense of wonder and curiosity that motivates all great scientific endeavors. The mystery continues, and the answers, when they finally come, will undoubtedly teach us something new about the remarkable universe we inhabit. Until then, KIC 8462852 remains a cosmic puzzle, a star that defies easy explanation and reminds us how much we still have to learn about the vast, complex, and endlessly surprising cosmos that surrounds us. Whether we're looking at the aftermath of a cosmic collision, the engineering project of an alien civilization, or some entirely new type of astrophysical phenomenon, KIC 8462852 has earned its place in the history of astronomical discovery. It stands as a testament to the power of careful observation, rigorous analysis, and the courage to pursue extraordinary explanations for extraordinary data. The star continues to dim and brighten in its mysterious patterns, 1,400 light-years away, carrying on its enigmatic dance while astronomers on Earth work tirelessly to understand its secrets. In that ongoing investigation lies the essence of scientific discovery, the patient pursuit of understanding in the face of cosmic mystery, the willingness to follow the data wherever it leads, and the recognition that the universe still holds wonders beyond our current comprehension. Perhaps that's the most important lesson KIC 8462852 has taught us. In an age when we sometimes feel that science has explained everything, when the universe seems mapped and cataloged and understood, this single star reminds us that mystery still exists. There are still questions without answers, phenomena without explanations, and discoveries waiting to be made. As you drift off to sleep tonight, consider that 1,400 light years away, KIC 8462852 continues its strange behavior, dimming and brightening in patterns that have confounded some of the brightest scientific minds of our time. Whether it represents alien engineering, cosmic catastrophe, or something entirely beyond our current imagination, it serves as a beacon of cosmic mystery in a universe that never stops surprising us. The light from that star, carrying its cryptic message of irregular dimming and mysterious behavior, continues its journey through space, just as it has for millennia. Some of that light, emitted during one of the star's dramatic dimming events, is traveling toward Earth right now, carrying information about whatever strange phenomenon occurred around that distant sun. When that light finally reaches us, years or decades from now, it may provide the final clue needed to solve the mystery, or perhaps it will only deepen the puzzle, revealing new complexities and contradictions that challenge our understanding even further. Either way, KIC 8462852 will continue to captivate and confound us, a single point of light in the cosmic darkness that holds secrets we are only beginning to fathom. In the meantime, the investigation continues, driven by the fundamental human need to understand our universe and our place within it. Each new observation brings us closer to the truth, whether that truth proves to be mundane or extraordinary. The star waits patiently in the depths of space, keeping its secrets while slowly revealing its mysteries to the patient astronomers who refuse to give up on understanding its bizarre behavior. And so, the story of KIC 8462852 continues, an ongoing dialogue between human curiosity and cosmic mystery, between our desire to understand and the universe's endless capacity to surprise us. It's a story that speaks to the very essence of what it means to be human in a vast and mysterious cosmos, forever searching for answers to questions we're only just learning how to ask. The technological revolution that KIC 8462852 sparked in astronomical observation cannot be overstated. Before its discovery, most stellar monitoring relied on detecting simple, predictable patterns. The star forced astronomers to develop entirely new analytical frameworks capable of handling chaotic, irregular data. Machine learning algorithms that had never been applied to stellar photometry suddenly became essential tools for understanding cosmic phenomena. The computational challenges were immense. Processing the massive datasets required to track hundreds of dimming events across multiple wavelengths pushed the limits of available computing resources. Universities and research institutions found themselves investing in supercomputing capabilities specifically to model the complex behavior of a single star 1,400 light-years away. These computational models revealed subtle patterns that human analysts had missed. Hidden periodicities emerged from the apparent chaos, suggesting underlying physical processes that operated on timescales ranging from days to decades. Some of these patterns seemed to repeat with mathematical precision that was almost unsettling in its regularity, while others showed the kind of complex fractal-like behavior that characterized chaotic dynamical systems. The fractal analysis was particularly intriguing because it suggested that whatever was happening around KIC 8462852 might be governed by the same mathematical principles that controlled weather systems, fluid turbulence, and other complex natural phenomena. If true, This would place the star's behavior within a well-understood theoretical framework, even if the specific physical mechanisms remained mysterious. However, the fractal interpretation faced significant challenges when confronted with the observed wavelength dependence of the dimming. Chaotic systems in astronomy typically affected all wavelengths equally, whereas KIC 8462852 showed the characteristic signature of small particle scattering. This wavelength selectivity suggested that the underlying chaos was being filtered through a very specific physical process involving dust or debris. The dust grain analysis became increasingly sophisticated as researchers applied techniques borrowed from atmospheric science and planetary astronomy. Different types of particles produced distinctive scattering signatures that could be identified through careful analysis of multi-wavelength observations. Silicate dust behaved differently from carbonaceous particles, which in turn had different properties from metallic grains or ice crystals. The spectroscopic analysis of light scattered by the material around KIC 8462852 revealed a complex mixture of particle types and sizes. There appeared to be populations of very fine dust, perhaps only nanometers across, mixed with larger grains that could be micrometers or even millimeters in diameter. This size distribution was unusual but not impossible for natural dust clouds created by cometary activity or collisional debris. More puzzling was the apparent lack of certain types of particles that would be expected in most astronomical dust environments. Observations showed little evidence for ice grains, despite the fact that comets typically contained large amounts of water ice. This absence suggested either that the dust was being heated to temperatures above the ice sublimation point, or that it had formed through processes that didn't involve significant amounts of ice. The heating hypothesis led researchers to examine the thermal environment around KIC 8462852 in unprecedented detail. The star's luminosity and spectral characteristics were well known, allowing precise calculations of the temperature that dust grains would reach at various distances from the star. These thermal models revealed that ice grains could only survive in the outer regions of the system, beyond several astronomical units from the star. If the dimming was caused by material in the outer system, this would explain the absence of ice signatures. However, it would also require the dust to be organized into structures that could transit across the star as seen from Earth, implying complex orbital dynamics that weren't easily explained by simple Keplerian motion. The orbital mechanics problem became a central focus of theoretical research into KIC 8462852. Computer simulations attempted to model how dust and debris could maintain the kind of complex, organized structures needed to produce the observed dimming patterns. These simulations required enormous computational resources and pushed the boundaries of what was possible with current modeling techniques. The most successful simulations involved multiple populations of particles with different orbital characteristics. Some dust appeared to be in relatively stable circular orbits, while other material followed highly eccentric paths that brought it close to the star during certain phases of its orbit. The interaction between these different populations created complex interference patterns that could potentially explain the observed variability. However, maintaining such a diverse population of orbital debris over extended periods proved to be extremely difficult in the simulations. Most configurations would evolve rapidly due to gravitational perturbations, collisional effects, and radiation pressure from the star. The system would either disperse completely or collapse into simpler, more regular structures that wouldn't produce the observed dimming patterns. This stability problem led some researchers to propose that KIC 8462852 might be experiencing ongoing replenishment of its circumstellar material. Perhaps a population of small bodies was continuously releasing dust through sublimation, collisions, or other physical processes. This ongoing production could maintain the complex orbital structure despite the various mechanisms that would otherwise cause it to decay. The continuous replenishment hypothesis gained support from observations of other stars with unusual variability. Several objects had been discovered that showed irregular dimming patterns, though none as extreme as KIC 8462852. These related stars suggested that the phenomenon might be more common than initially thought, representing a previously unrecognized class of stellar systems. The discovery of additional anomalous stars provided crucial comparative data for testing theoretical models. Each new object offered slightly different characteristics that helped constrain the range of possible explanations. Some showed predominantly periodic variability, others were more chaotic, and a few displayed the kind of complex structured dimming that characterized KIC 8462852. Statistical analysis of this growing sample revealed interesting correlations between stellar properties and variability characteristics. Stars with certain masses, ages, and spectral types seemed more likely to exhibit unusual dimming behavior. These correlations provided important clues about the underlying physical processes and helped researchers identify promising targets for future observations. The age correlation was particularly intriguing because it suggested that the phenomenon might be related to specific phases of stellar evolution. Young stars were known to be surrounded by protoplanetary disks that could produce complex variability, but KIC 8462852 was clearly not a young object. Instead, it appeared to be a mature middle-aged star that should have long since cleared its immediate environment of primordial debris. This raised the possibility that KIC 8462852 was experiencing some form of late-stage evolutionary process that wasn't well understood. Perhaps the star was beginning to shed material from its outer layers, creating a circumstellar envelope that could produce the observed dimming. Alternatively, the system might be undergoing tidal disruption of small bodies that had survived from the early phases of planetary formation. The planetary formation connection led researchers to examine KIC 8462852 for evidence of planets or other massive bodies that could influence the dynamics of circumstellar material. Radial velocity measurements, which could detect the gravitational wobble caused by orbiting planets, were conducted using the most sensitive spectrographs available. These planet-hunting observations revealed no clear evidence for large planets in close orbits around KIC 8462852. However, the measurements weren't sensitive enough to detect smaller planets or objects in distant orbits. It remained possible that the system contained planets that were influencing the behavior of circumstellar dust without being directly detectable through current techniques. The absence of obvious planetary signatures didn't rule out gravitational influence from unseen objects. Theoretical models showed that even relatively small bodies could have significant effects on dust dynamics if they were located in the right orbital configurations. Resonant interactions between dust particles and planets could create exactly the kind of complex, structured patterns observed in the dimming events. These resonance models drew inspiration from similar phenomena observed in the solar system, where the gravitational influence of planets created gaps, rings, and other structures in asteroid and debris populations. The asteroid belt, for example, showed clear evidence of orbital resonances with Jupiter that had shaped its structure over billions of years. Applying these concepts to KIC 8462852 required scaling up the models to account for the much larger distances and different physical conditions around the star. The calculations were extremely complex and required sophisticated numerical techniques to track the long-term evolution of millions of dust particles under the combined influence of stellar radiation, gravitational perturbations, and mutual collisions. The most promising resonance models involved multiple planets in carefully tuned orbital configurations that could maintain stable dust structures over extended periods. These configurations were rare and required very specific initial conditions, but they could potentially explain both the complexity and the apparent stability of the observed dimming patterns. However, the resonance models face the same fundamental problem as other explanations. They required enormous amounts of dust to produce the observed dimming depths. Even efficient gravitational concentration mechanisms couldn't easily account for the sheer quantity of material needed to block 20% of a star's light. This material problem led some researchers to reconsider the basic assumptions about the dimming mechanism itself. Perhaps the observations weren't being caused by simple occultation of the star by opaque material. Alternative mechanisms, such as gravitational lensing, scattering by exotic particles, or even relativistic effects, might be capable of producing similar observational signatures with much less material. The gravitational lensing hypothesis was particularly intriguing because it could potentially amplify small effects into large apparent brightness changes. If KIC 8462852 were being lensed by a massive, dark object moving across our line of sight, it could create exactly the kind of irregular, complex light curves that had been observed. However, gravitational lensing effects typically produced characteristic signatures that were absent from the KIC 8462852 data. Lensing events usually showed symmetric brightness variations with specific time evolution patterns that didn't match the observed dimming episodes. Moreover, the wavelength dependence of the dimming was inconsistent with achromatic gravitational effects. The exotic particle hypothesis proposed that the dimming might be caused by clouds of unusual material with properties unlike conventional astronomical dust. Perhaps the star was encountering regions of dark matter that could interact with photons through unknown physical processes. Alternatively, the system might contain populations of magnetic monopoles, axions, or other hypothetical particles that could affect the propagation of starlight. While these exotic explanations were theoretically possible, they required invoking physics beyond the standard model and had no supporting evidence from other astronomical observations. The scientific principle of parsimony suggested that conventional explanations should be exhausted before considering such speculative alternatives. The electromagnetic interaction hypothesis focused on the possibility that charged particles around KIC 8462852 might be affecting the star's light through plasma physics effects rather than simple geometric occultation. If the circumstellar environment contained significant amounts of ionized gas, it could potentially create complex optical effects that mimicked the behavior of solid particles. Plasma physics offered several mechanisms that could produce wavelength-dependent dimming similar to what was observed around KIC 8462852, scattering by free electrons, absorption by ionized atoms, and various collective plasma phenomena could all contribute to apparent brightness variations that would be difficult to distinguish from dust-based explanations using current observational techniques. The plasma hypothesis had the advantage of potentially explaining the absence of strong infrared emission during dimming events. Ionized gas wouldn't necessarily emit significant amounts of thermal radiation, unlike solid dust particles that would be heated by absorbed starlight. However, plasma-based models face their own challenges in explaining the complex, structured nature of the observed dimming patterns. As observational techniques continued to improve throughout the early 2020s, new types of measurements became possible that promised to discriminate between different theoretical models. Polarization observations could reveal the properties of scattering particles with unprecedented precision. Interferometric techniques could potentially resolve spatial structure in the circumstellar environment. Advanced spectroscopic methods could detect subtle signatures of specific particle compositions or plasma conditions. The polarization studies proved particularly valuable because different types of particles produced distinctive polarization signatures when they scattered starlight. Spherical dust grains behaved differently from elongated particles. Metallic materials had different properties from silicates, and large particles created different patterns from small ones. Initial polarization observations of KIC 8462852 during dimming events revealed complex, time-variable polarization signatures that suggested a mixture of particle types and orientations. The polarization varied not only with wavelength, but also changed throughout individual dimming events, indicating that the scattering material had complex spatial and temporal structure. These polarization results provided strong support for dust-based explanations, while ruling out many exotic alternatives. The observations were consistent with clouds of small, irregularly shaped particles that were aligned by magnetic fields or other organizing forces. The alignment mechanism remained unclear, but it represented another layer of complexity in an already complicated system. The magnetic field hypothesis opened new avenues for theoretical research into KIC 8462852. Stars like KIC 8462852 were known to possess magnetic fields, and these fields could potentially organize circumstellar dust into complex structures. Magnetic forces could trap charged particles, align dust grains, and create long-lived configurations that might explain the observed dimming patterns. Computer simulations of magnetohydrodynamic processes around KIC 8462852 revealed that stellar magnetic fields could indeed create stable dust structures under certain conditions. The calculations showed that charged dust grains could be confined to specific orbital regions where magnetic forces balanced gravitational and radiation pressure effects. These magnetic confinement models offered potential solutions to several puzzles surrounding KIC 8462852. They could explain the apparent stability of the dust structures over long periods. They could account for the complex, organized nature of the dimming patterns, and they could potentially explain why the phenomenon appeared to be so rare among stars of similar type. However, the magnetic models required the dust particles to be electrically charged, which wasn't guaranteed for all types of circumstellar material. The charging mechanisms that could operate around KIC 8462852 needed to be strong enough to overcome the tendency of dust grains to remain electrically neutral through recombination processes. The dust charging problem led researchers to investigate the high-energy environment around KIC 8462852 in greater detail. While the star appeared normal in most respects, subtle variations in its output of ultraviolet radiation or charged particles could potentially create the conditions needed for efficient dust charging. X-ray observations of KIC 8462852 using space-based telescopes revealed no obvious signs of unusual high-energy activity. The star's X-ray output was typical for its spectral class and showed no correlation with the dimming events. This finding suggested that if magnetic effects were important, they were operating through subtle processes that didn't require extreme stellar activity. The search for magnetic signatures in the system extended to radio observations, which could potentially detect synchrotron emission from charged particles moving in magnetic fields. Radio telescopes around the world were directed toward KIC 8462852, scanning across a wide range of frequencies for any signs of non-thermal emission. These radio observations yielded mostly null results, though some showed hints of very weak emission that might be consistent with low-level magnetic activity. The signals were at the limit of instrumental sensitivity and required careful analysis to distinguish from background noise and interference from terrestrial sources. The marginal radio detections were intriguing but not conclusive. They suggested that some form of magnetic activity might be present around KIC 8462852, but the evidence wasn't strong enough to definitively confirm the magnetic dust trapping hypothesis. More sensitive observations would be needed to establish whether magnetic effects played a significant role in the system's behavior. As the investigation of KIC 8462852 entered its second decade, the accumulated body of evidence had eliminated many proposed explanations while highlighting the extraordinary nature of whatever process was actually occurring. The star continued to defy easy categorization, representing a phenomenon that seemed to exist at the boundary between conventional stellar astronomy and exotic astrophysics. The persistence of the mystery had profound implications for our understanding of stellar systems and the diversity of phenomena that could occur in the universe. KIC 8462852 demonstrated that even after centuries of astronomical observation, nature could still produce surprises that challenged fundamental assumptions about how stars and their environments behaved. The star also served as a powerful reminder of the importance of systematic, long-term astronomical surveys. Without the continuous monitoring provided by the Kepler mission, the unusual behavior of KIC 8462852 would never have been detected. This lesson influenced the design of future space missions and ground-based survey programs that aim to discover similar anomalous objects. The technological legacy of KIC 8462852 extended far beyond astronomy into fields like data science, machine learning, and signal processing. The techniques developed to analyze the star's complex variability found applications in areas ranging from climate modeling to financial market analysis. The star had inadvertently driven innovation across multiple scientific disciplines. The collaborative aspects of the KIC 8462852 investigation also established new models for conducting large-scale scientific research. The partnership between professional astronomers and citizen scientists had proven remarkably effective, demonstrating the value of distributed observational networks and crowdsourced data analysis. This collaborative approach was particularly important for studying transient phenomena like the dimming events around KIC 8462852. Professional telescopes had limited time available for monitoring any single object, but networks of amateur observers could provide continuous coverage that would be impossible to achieve through traditional means. The success of citizen science in the KIC 8462852 investigation inspired similar collaborative efforts for other astronomical projects. Distributed networks of small telescopes began monitoring other anomalous stars, searching for additional examples of unusual variability that might provide comparative data for understanding the phenomenon. These follow-up surveys discovered several stars with behavior reminiscent of KIC 8462852, though none showed the extreme characteristics that made the original object so remarkable. The new discoveries suggested that irregular stellar variability might be more common than previously thought, representing a spectrum of phenomena ranging from subtle to dramatic. The growing sample of anomalous stars provided valuable statistical data for testing theoretical models. Researchers could now examine correlations between stellar properties, system characteristics, and variability patterns across multiple objects. This comparative approach offered new insights into the underlying physical processes that might be responsible for the observed behavior. One particularly important discovery was that most of the anomalous stars were located in specific regions of the galaxy, suggesting that environmental factors might play a role in determining which systems developed unusual variability. This spatial clustering provided clues about the external influences that could trigger or sustain the phenomenon. The galactic environment hypothesis proposed that KIC 8462852 and similar stars might be encountering dense regions of interstellar dust or debris that created the observed dimming effects. As stars moved through the galaxy, they would occasionally pass through clouds of material left over from ancient stellar explosions or other cosmic events. This environmental explanation had several attractive features. It could account for the rarity of the phenomenon, since most stars wouldn't encounter dense enough material clouds to produce detectable effects. It could explain the temporal evolution of the dimming patterns as the star gradually moved through regions of varying density, and it could potentially account for the complex structure observed in the dimming events. However, the environmental hypothesis faced significant challenges when confronted with detailed observations of KIC 8462852. The star showed no signs of the bow shock or other features that would be expected if it were plowing through dense interstellar material at high speed. Moreover, the dimming patterns showed evidence of periodicity that suggested gravitationally bound material rather than randomly distributed interstellar dust. The bound material requirement led researchers back to circumstellar explanations, but with a new focus on the long-term evolution of planetary systems. Perhaps KIC 846285 was experiencing a phase of its evolution where previously stable populations of small bodies were being destabilized and creating the observed dust clouds. This late-stage instability hypothesis drew parallels with phenomena observed in the outer solar system, where the Kuiper belt and Oort cloud represented reservoirs of small bodies that could potentially be disrupted by external influences. If KIC 846285 possessed similar reservoirs that were currently being disturbed, it could explain the ongoing production of circumstellar dust. The destabilization mechanism could involve various external triggers, from passing stars to encounters with dense molecular clouds. The galaxy was a dynamic environment where stellar systems regularly experienced gravitational perturbations that could affect the stability of weakly bound objects in their outer regions. Computer simulations of stellar encounters with KIC 846285 showed that relatively close approaches by other stars could indeed destabilize populations of comets and asteroids in the outer system. These gravitational disturbances could send showers of small bodies into the inner system, where they would sublimate and fragment to create the observed dust clouds. The stellar encounter hypothesis required that KIC 846285 had recently experienced such a close approach within the last few thousand to million years. While such encounters were rare for any individual star, they occurred regularly on galactic timescales and could potentially explain the observed rarity of the phenomenon. However, identifying the specific stellar encounter that might have triggered the current activity around KIC 846285 proved extremely difficult. The galactic neighborhood of the star was well mapped, and no obvious candidates for recent close approaches were apparent from current stellar motions and positions. This apparent absence of trigger events led some researchers to propose internal rather than external causes for the instability around KIC 846285. Perhaps the star itself was undergoing subtle changes that affected the dynamics of its planetary system. Small variations in stellar luminosity, magnetic field strength, or mass loss could potentially destabilize previously stable orbital configurations. The internal trigger hypothesis was harder to test observationally because the proposed stellar changes would be very subtle and difficult to detect with current instruments. However, it offered a way to explain the phenomenon without requiring improbable external coincidences or encounters. As the 2020s progressed, new observational capabilities continued to provide fresh insights into the nature of KIC 846285. The James Webb Space Telescope's unprecedented infrared sensitivity allowed detailed characterization of the dust around the star during dimming events. These observations revealed complex temperature and composition structures that provided new constraints on theoretical models. The Webb observations showed that the dust around KIC 846285 had a complex thermal structure with different temperature components that suggested multiple populations of particles at various distances from the star. This thermal complexity was consistent with dust clouds that extended over large spatial scales, supporting models that involved disrupted comets or collision debris. More surprisingly, the infrared spectra revealed evidence for crystalline silicate particles, which typically formed at high temperatures close to stars. The presence of these hot dust minerals in material that appeared to be located far from KIC 846285 suggested a complex thermal history that wasn't easily explained by simple models. The crystalline silicate discovery led researchers to reconsider the formation mechanisms for the dust around KIC 846285. Perhaps the material had been processed through multiple heating and cooling cycles, possibly through repeated close approaches to the star or through collisional processing that could generate high temperatures. These new infrared observations also provided more precise measurements of the total amount of dust around KIC 8462852. The estimates confirmed that enormous quantities of material were required to produce the observed dimming, equivalent to hundreds or thousands of large comets worth of dust and debris. The sheer scale of the material requirements continued to pose challenges for all proposed explanations. Whether the dust came from disrupted comets, collisional debris, or some other source, the quantities involved represented a significant fraction of the total solid material that would typically be available in a mature stellar system. This material budget problem led some researchers to propose that KIC 8462852 might be an unusually massive or resource-rich system that could sustain high levels of dust production over extended periods. Alternatively, the dust might be the result of a truly catastrophic event that had released enormous amounts of material in a single episode. The catastrophic event hypothesis gained support from studies of the dust composition and structure. The complex mixture of particle types and sizes observed around KIC 8462852 was consistent with the aftermath of a major collision between large planetary bodies, which could have produced the diverse debris population needed to explain the observations. However, the timing requirements for this scenario remained problematic. A single catastrophic collision would be expected to produce a debris cloud that would evolve and disperse over time, yet KIC 8462852 had shown relatively stable dimming behavior over more than a decade of observations. This stability suggested that either the catastrophic event was very recent, occurring within the last few centuries, or that some ongoing process was maintaining the dust cloud against dispersive forces. Both possibilities required specific conditions that would be rare in typical stellar systems. The maintenance mechanism problem led researchers to investigate active dust production processes that could continuously replenish the material around KIC 8462852. Perhaps populations of small bodies were undergoing ongoing fragmentation and sublimation that could sustain the observed dust levels over extended periods. This active production scenario drew inspiration from observations of active asteroids and main belt comets in the solar system, where small bodies were observed to undergo spontaneous fragmentation or outgassing that created temporary dust clouds. If KIC 8462852 possessed large populations of such active objects, it could potentially maintain high dust levels indefinitely. The active object hypothesis required specific environmental conditions that could trigger and sustain fragmentation or outgassing in populations of small bodies. These conditions might include thermal cycling, tidal stresses, or impacts from smaller projectiles that could cause larger objects to break apart or release dust. Computer models of active small body populations showed that under the right circumstances, such systems could indeed produce sustained dust clouds with properties similar to those observed around KIC 8462852. However, these models required carefully tuned parameters and specific orbital configurations that might be rare in nature. The rarity requirement brought the investigation full circle to the fundamental question of why KIC 8462852 appeared to be so unique among the hundreds of thousands of stars observed by various astronomical surveys. This uniqueness suggested that either the underlying phenomenon was extremely rare or that special observational circumstances made KIC 8462852 visible while similar objects remained hidden. The observational selection effects were difficult to quantify because they depended on complex factors, including the orientation of circumstellar structures, the timing of observations relative to dust production events, and the sensitivity limits of different survey techniques. It was possible that many more stars like KIC 8462852 existed but hadn't been detected due to unfavorable observing conditions. This possibility motivated expanded surveys designed specifically to search for similar objects using optimized detection techniques. Machine learning algorithms trained on the KIC 8462852 light curves were applied to massive databases of stellar observations, looking for other examples of complex, irregular variability. These systematic searches discovered a handful of additional candidates with some similarities to KIC 8462852, though none showed the extreme characteristics of the original object. The new discoveries suggested that the phenomenon might represent a spectrum of activity levels, with KIC 8462852 representing an unusually active example of a more general class of objects. The discovery of related objects provided crucial comparative data for testing theoretical models. Each new example offered slightly different characteristics that helped constrain the range of possible explanations and identify the physical processes that were most important for producing the observed behavior. Statistical analysis of the growing sample revealed correlations between stellar properties and the characteristics of circumstellar variability. Stars with certain masses, ages, and metallicities seemed more likely to show irregular dimming behavior, providing clues about the conditions required for the phenomenon to develop. These correlations suggested that the unusual behavior around KIC 8462852 might be related to specific phases of stellar or planetary system evolution that occurred only under particular circumstances. This evolutionary connection offered hope for eventually understanding the phenomenon through detailed studies of stellar and planetary formation processes. As the investigation of KIC 8462852 entered its 15th year, the accumulated evidence had painted a picture of a truly extraordinary object that continued to challenge our understanding of stellar systems. While many proposed explanations had been ruled out or shown to have serious problems, the core mystery remained unsolved. The star had become a landmark case in astronomy, demonstrating both the power and the limitations of observational science. It showed how careful, systematic observations could reveal phenomena that were completely unexpected and poorly understood. At the same time, it illustrated how even extensive datasets and sophisticated analysis techniques might not be sufficient to definitively solve complex astrophysical puzzles. The broader impact of KIC 8462852 extended beyond the specific question of what was causing its unusual dimming. The star had driven technological innovation, inspired new theoretical frameworks, and established new standards for astronomical investigation. It had shown the value of long-term monitoring, international collaboration, and interdisciplinary research approaches. Perhaps most importantly, KIC 8462852 had reminded the scientific community that the universe still held profound mysteries that could surprise and confound even our most advanced theoretical understanding. In an era when many astronomical phenomena seemed well explained by established physics, this single star represented a frontier where new discoveries and new physics might still be waiting to be found. The ongoing investigation of KIC 8462852 continues to this day, with new observations and analysis techniques constantly being applied to the growing dataset. Each new piece of evidence brings us incrementally closer to understanding this cosmic enigma, even as it sometimes reveals new complexities that deepen the mystery. The star persists in its strange behavior, 1,400 light-years away, continuing its irregular dance of dimming and brightening while astronomers on Earth work tirelessly to decode its secrets. Whether the ultimate explanation proves to be a natural phenomenon we don't yet understand, or something even more extraordinary, KIC 8462852 has already earned its place as one of the most important and mysterious objects in the modern astronomical catalog. In the quiet moments between observations, when telescopes around the world pause in their ceaseless scanning of the heavens, KIC 8462852 continues its enigmatic performance. The star that defied every scientific theory remains defiant still, a cosmic puzzle that reminds us how much we have yet to learn about the universe we call home. The philosophical implications of KIC 846-2852 extend far beyond the technical details of its unusual behavior. The star has forced humanity to confront fundamental questions about the nature of scientific knowledge and the limits of our understanding. Here was an object that clearly existed, that could be observed and measured with unprecedented precision, yet defied all attempts at satisfactory explanation. This confrontation with the inexplicable has deep roots in the history of scientific discovery. Throughout the centuries, astronomers have encountered phenomena that challenged prevailing theories and forced revolutionary changes in our understanding of the cosmos. The precession of Mercury's orbit eventually led to general relativity. The missing mass in galaxy clusters revealed the existence of dark matter. Now, KIC 846-2852 represented another such watershed moment where observations demanded new theoretical frameworks. The star's resistance to explanation had a humbling effect on the astronomical community. After decades of remarkable progress in understanding stellar physics, exoplanets, and galactic structure, KIC 846-2852 served as a reminder that nature still possessed the power to surprise us. It demonstrated that even our most sophisticated models and theories might be incomplete or fundamentally flawed. This humility was reflected in the increasingly diverse approaches that researchers took to studying the star. Traditional astronomical methods were supplemented with techniques borrowed from fields as varied as chaos theory, materials science, and even archaeology. The interdisciplinary nature of the investigation reflected a growing recognition that complex phenomena might require equally complex analytical approaches. The archaeological analogy was particularly apt because studying KIC 846-2852 often felt like examining artifacts from an unknown civilization. The dimming patterns contained information about processes and structures that had occurred in the distant past, encoded in light that had traveled across interstellar space for over a millennium. Deciphering this information required skills similar to those used by archaeologists interpreting ancient texts or artifacts. The temporal aspect of the observations added another layer of complexity to the investigation. The light curves from KIC 846-2852 represented a historical record spanning years of activity around the star, but this record was incomplete and fragmentary. Large gaps in the observational coverage meant that crucial events might have been missed, while the irregular timing of dimming episodes made it difficult to predict when future activity might occur. This temporal uncertainty had profound implications for planning observational campaigns. Unlike predictable phenomena such as planetary transits or stellar eclipses, the dimming events around KIC 846-2852 could only be observed opportunistically when they happened to occur. This unpredictability placed enormous demands on observational resources and required flexible scheduling that could respond rapidly to unexpected developments. The global coordination required for effective monitoring of KIC 846-2852 represented a remarkable achievement in international scientific collaboration. Telescopes on different continents worked together to provide continuous coverage as the Earth's rotation carried individual observatories in and out of darkness. This follow-the-sun approach ensured that the star could be monitored around the clock during active periods. The coordination challenges were immense, involving dozens of observatories with different capabilities, schedules, and priorities. Communication protocols had to be established to alert the global community when dimming events were detected. Data sharing agreements were negotiated to ensure that observations from multiple telescopes could be combined and analyzed collectively. The success of this collaborative approach demonstrated the power of international cooperation in tackling complex scientific problems. KIC 846-2852 had effectively created a new model for astronomical research that transcended national boundaries and institutional affiliations. The star had become a unifying focus for the global astronomical community, bringing together researchers who might never have collaborated otherwise. The educational impact of KIC 8462852 extended from elementary schools to graduate programs in astrophysics. The star's mysterious behavior captured the imagination of students at all levels, providing a compelling example of how science confronted the unknown. Teachers used the story of KIC 8462852 to illustrate fundamental concepts in astronomy, physics, and scientific methodology. The star's journey from discovery to ongoing investigation provided a perfect case study in the scientific process. Students could follow the development of hypotheses, the design of observational tests, and the revision of theories in response to new evidence. They could see how science actually worked, not as a collection of facts to be memorized, but as a dynamic process of inquiry and discovery. Graduate students and early career researchers found in KIC 8462852 a unique opportunity to work on a problem that was genuinely unsolved. Unlike many thesis projects that involved incremental advances in well-established fields, research on KIC 8462852 offered the possibility of making truly groundbreaking discoveries. This attracted some of the brightest young minds in astronomy to work on the problem. The career impact for researchers associated with KIC 8462852 was significant and generally positive. The high-profile nature of the discovery and the media attention it generated provided unprecedented visibility for astronomical research. Scientists who might otherwise have labored in obscurity found themselves giving interviews to major news outlets and popular science magazines. However, the attention also created challenges. The pressure to provide definitive answers to persistent media questions sometimes conflicted with the necessarily cautious and methodical approach of scientific investigation. Researchers had to learn to communicate uncertainty and ambiguity to audiences that preferred clear, simple explanations. The funding implications of KIC 8462852 were substantial and far-reaching. The star's mysterious behavior generated public interest that translated into political and financial support for astronomical research. Funding agencies found it easier to justify investments in astronomy when they could point to specific, compelling mysteries that captured public imagination. This increased support extended beyond direct research on KIC 8462852 to broader investments in astronomical infrastructure. New telescopes, improved instrumentation, and enhanced data analysis capabilities were funded partly on the argument that they would help solve mysteries like KIC 8462852. The star had effectively become a poster child for the need for continued investment in astronomical research. The technological spin-offs from KIC 8462852 research were numerous and often unexpected. The advanced data analysis techniques developed to study the star's light curves found applications in fields ranging from medical imaging to financial market analysis. The machine learning algorithms trained on stellar variability data were adapted for use in climate modeling, earthquake prediction, and industrial quality control. The photometric techniques refined for KIC 8462852 observations improved the precision of measurements across all of astronomy. Methods for removing instrumental artifacts, correcting for atmospheric effects, and combining data from multiple telescopes were enhanced and standardized. These improvements benefited not only research on anomalous stars, but the entire field of time domain astronomy. The citizen science aspects of the KIC 8462852 investigation had particularly far-reaching implications for how astronomical research was conducted. The successful participation of amateur astronomers in professional-grade observations challenged traditional boundaries between professional and amateur science. It demonstrated that important contributions could come from unexpected sources. This democratization of astronomical research was enabled by advances in technology that made sophisticated observations possible with relatively modest equipment. Digital cameras, computerized telescopes, and internet connectivity had created opportunities for participation that didn't exist in previous generations. KIC 8462852 became a test case for this new model of distributed, collaborative research. The amateur contributions to KIC 8462852 research weren't limited to observations. Citizen scientists participated in data analysis, hypothesis generation, and even theoretical modeling. Online platforms allowed volunteers to examine light curves, identify patterns, and propose explanations alongside professional researchers. This crowdsourced approach to scientific investigation proved remarkably effective. The success of citizen science in astronomy inspired similar approaches in other fields. Biology, climate science, and archaeology began experimenting with crowdsourced research models that had been pioneered in the study of KIC 8462852. The star had inadvertently catalyzed a broader transformation in how science was conducted in the digital age. The cultural impact of KIC 8462852 extended well beyond the scientific community into popular culture, literature, and philosophy. The star appeared in science fiction novels, inspired documentary films, and became the subject of countless online discussions and conspiracy theories. Its mysterious behavior captured the public imagination in ways that few astronomical discoveries had achieved. Science fiction writers found in KIC 8462852 a perfect vehicle for exploring themes of alien intelligence, cosmic mystery, and the limits of human understanding. The star's real-world enigmatic behavior provided a solid foundation for speculative fiction that didn't require authors to invent implausible scenarios. Reality had already provided something more mysterious than most fiction. The philosophical implications of KIC 8462852 resonated particularly strongly with those interested in the search for extraterrestrial intelligence. Even if the star's behavior ultimately proved to have natural explanations, it demonstrated that genuinely anomalous phenomena could exist in the universe. This possibility kept alive hopes that other anomalies might indeed represent evidence of alien civilizations. The SETI community embraced KIC 8462852 as validation of their broader mission, even as specific explanations involving alien technology became less favored. The star had shown that careful astronomical observations could potentially detect signs of advanced civilizations, providing proof of concept for technosignature searches, even if this particular example didn't pan out. The methodology developed for investigating KIC 8462852 became a template for future SETI research. The systematic approach of eliminating natural explanations before considering artificial ones, the importance of independent confirmation, and the need for multiple types of observations all became standard practices in the search for technosignatures. This methodological legacy extended beyond SETI to influence how astronomers approached any unusual or anomalous observations. The KIC 8462852 investigation had established rigorous standards for extraordinary claims, requiring extraordinary evidence and systematic elimination of conventional explanations before considering exotic alternatives. The statistical lessons learned from KIC 8462852 were particularly important for understanding the significance of rare events in astronomy. The star had demonstrated that truly unusual phenomena could occur naturally, even if they were so rare that only one example was known among hundreds of thousands of observed objects. This rarity didn't necessarily make them artificial or impossible. These statistical insights influenced how astronomers interpreted other anomalous observations. The tendency to dismiss unusual data as instrumental artifacts or processing errors was tempered by the recognition that nature could indeed produce phenomena that seemed impossible according to current understanding. KIC 8462852 had taught researchers to take anomalies seriously while maintaining appropriate skepticism. The data preservation and sharing practices developed for KIC 8462852 research set new standards for astronomical data management. The recognition that this might be a once-in-a-lifetime discovery motivated extraordinary efforts to preserve and document every aspect of the observations. Raw data, processing algorithms, and analysis results were archived with unprecedented care and completeness. This attention to data preservation proved prescient as new analysis techniques were developed years after the initial observations. Researchers could apply sophisticated algorithms that hadn't existed when the data was first collected, extracting new information from archived observations. The careful documentation of data processing steps ensured that these reanalyses could be conducted with full understanding of potential systematic effects. The open data policies adopted for KIC 8462852 research encouraged broader participation in the investigation while establishing new norms for scientific transparency. Making raw data freely available allowed independent researchers to verify results, develop alternative analysis approaches, and pursue novel lines of investigation that the original observers might not have considered. This transparency had the additional benefit of maintaining public trust in the scientific process. When extraordinary claims were made about KIC 8462852, skeptics could examine the underlying data themselves rather than simply accepting or rejecting conclusions based on authority. This openness helped maintain the credibility of the research even when definitive explanations remained elusive. The peer review processes surrounding KIC 8462852 research evolved to accommodate the unique challenges posed by studying genuinely novel phenomena. Traditional peer review relied heavily on comparison with similar previous work, but KIC 8462852 had no real precedence. Reviewers had to develop new criteria for evaluating research on unprecedented observations. This evolution in peer review standards influenced how the scientific community evaluated other potentially groundbreaking discoveries. The KIC 8462852 papers established precedents for how to present and evaluate research on anomalous phenomena, balancing the need for rigorous skepticism with openness to genuinely new possibilities. The international conferences and workshops organized around KIC 8462852 created new forums for scientific collaboration and discussion. These meetings brought together researchers from diverse fields who might not otherwise interact, fostering interdisciplinary approaches to complex problems. The conferences became models for how the scientific community could organize around specific challenging questions. The social dynamics of KIC 8462852 research reflected broader trends in how science was conducted in the internet age. Online collaboration tools allowed researchers from around the world to work together in real time, sharing data, ideas, and analysis results almost instantaneously. The traditional model of scientific collaboration based on personal relationships and institutional affiliations was supplemented by new forms of networked research. The media coverage of KIC 8462852 evolved substantially over the years of investigation. Initial reports focused heavily on the possibility of alien megastructures, reflecting both public fascination with extraterrestrial life and the media's tendency to emphasize dramatic possibilities. As evidence accumulated favoring natural explanations, coverage became more nuanced and technically sophisticated. This evolution in media coverage paralleled broader changes in science communication. The KIC 8462852 story demonstrated the challenges of communicating ongoing scientific investigations to public audiences accustomed to definitive answers. Journalists and scientists learned to better convey the inherent uncertainty and iterative nature of the research process. The impact of social media on KIC 8462852 research was profound and multifaceted. Platforms like Twitter and Reddit allowed rapid dissemination of new observations and analysis results, enabling faster collaboration and discussion than traditional publication channels. However, social media also amplified speculation and misinformation, creating challenges for maintaining scientific rigor in public discussions. The rise of preprint servers and open access publishing during the KIC 846-2852 investigation period transformed how research results were shared and discussed. Important findings could be communicated to the scientific community within days of discovery rather than waiting months for traditional peer review and publication. This acceleration enabled more rapid progress, but also required new approaches to quality control. The economic impact of KIC 846-2852 extended beyond direct research funding to influence broader technology development and commercial applications. Companies developing advanced optical systems, data analysis software, and precision manufacturing capabilities found new markets in the astronomical research community, motivated by stars like KIC 846-2852. The telescope and instrumentation industries benefited from increased demand for high-precision photometric systems capable of detecting subtle brightness variations. Small companies specializing in astronomical equipment found new opportunities as amateur astronomers sought to participate in professional-grade observations of anomalous stars. The software industry developed new products specifically for astronomical time series analysis, machine learning applications in astronomy, and collaborative research platforms. These tools found applications beyond astronomy, contributing to a broader ecosystem of data analysis and scientific collaboration software. The insurance and risk assessment industries took note of KIC 846-2852 as an example of how seemingly impossible events could nonetheless occur. The star's behavior challenged conventional approaches to estimating the probability of rare events, influencing how analysts thought about tail risks and black swan phenomena in various domains. The psychological impact of KIC 846-2852 on the astronomical community was subtle but significant. Many researchers experienced a renewed sense of wonder and humility when confronted with phenomena that defied explanation. The star reminded scientists why they had been drawn to astronomy in the first place: the opportunity to explore the unknown and make genuine discoveries. This psychological renewal was particularly important for a field that had become increasingly focused on incremental advances and large-scale statistical studies. KIC 846-2852 represented a return to the tradition of individual mysterious objects that could capture the imagination and drive innovation through focused investigation. The stress and frustration of working on an apparently unsolvable problem also affected researchers involved in KIC 846-2852 studies. The pressure to find explanations, combined with the high-profile nature of the investigation, created psychological challenges that weren't typical of most astronomical research. Support networks and collaborative approaches helped researchers cope with these pressures. The career trajectories of early career researchers associated with KIC 846-2852 were profoundly influenced by their involvement in the investigation. Many found that their association with the discovery opened doors and created opportunities that might not otherwise have been available. However, some also experienced challenges when the initial dramatic hypotheses gave way to more mundane explanations. The training and education of new astronomers was transformed by the KIC 846-2852 experience. Graduate programs began emphasizing skills in time series analysis, machine learning, and collaborative research that had proven essential for studying anomalous stellar behavior. The star had effectively defined a new set of core competencies for 21st century astronomers. The instrument development driven by KIC 846-2852 research pushed the boundaries of what was technically feasible in ground-based and space-based astronomy. New detector technologies, adaptive optic systems, and data processing pipelines were developed to extract maximum information from observations of the star and similar objects. These technological advances had applications far beyond the study of anomalous stars. Improved photometric precision benefited exoplanet detection, stellar astrophysics, and cosmological measurements. Enhanced data analysis capabilities found uses throughout astronomy and other data-intensive fields. The computational challenges posed by KIC 8462852 drove advances in high-performance computing and algorithm development. The need to process massive data sets and run complex simulations pushed researchers to develop more efficient algorithms and leverage emerging technologies like graphics processing units and cloud computing platforms. The archives of KIC 8462852 data became valuable resources for testing new analysis techniques and training machine learning algorithms. The well-characterized nature of the observations provided benchmark datasets that could be used to validate new methods before applying them to other astronomical problems. The theoretical physics community embraced KIC 8462852 as a test case for exotic phenomena that might not be observable elsewhere in the universe. While most explanations focused on conventional astrophysics, the star's unusual behavior provided motivation for exploring more speculative possibilities involving new physics. Some theoretical physicists proposed that KIC 8462852 might be influenced by phenomena related to dark matter, extra dimensions, or modified gravity theories. While these ideas remained highly speculative, they demonstrated how anomalous observations could inspire fundamental physics research even when conventional explanations seemed more likely. The astrochemistry community found in KIC 8462852 an opportunity to study dust formation and evolution processes under unusual conditions. The complex mixture of particle types and sizes inferred from observations provided insights into chemical processes that might occur during planetary formation or destruction. The dust composition studies revealed trace elements and isotopic ratios that provided clues about the formation history of the circumstellar material. These chemical fingerprints helped constrain models of dust production and evolution, contributing to broader understanding of how solid materials formed and evolved in planetary systems. The plasma physics community contributed sophisticated models of how ionized gas might behave in the environment around KIC 8462852. While plasma-based explanations were less favored than dust models, the theoretical work contributed to understanding of magnetospheric processes and stellar wind interactions. The astrobiology implications of KIC 8462852 extended beyond the specific question of whether it represented alien technology. The star demonstrated that genuinely unusual phenomena could occur in the universe, expanding the range of possibilities that astrobiologists needed to consider when thinking about how life might manifest itself on cosmic scales. Even natural explanations for KIC 8462852's behavior had astrobiological implications. If the star was surrounded by the debris of destroyed planets, it raised questions about the long-term stability of planetary systems and the survival prospects for any life they might harbor. The star served as a reminder that planetary systems could experience catastrophic events that would eliminate any biological inhabitants. The search for biosignatures in the spectra of exoplanets was influenced by lessons learned from KIC 8462852. The star demonstrated the importance of understanding all possible natural explanations for unusual observations before invoking biological or technological interpretations. This methodological lesson became incorporated into protocols for biosignature detection. The galactic astronomy community used KIC 8462852 as a case study for understanding how stellar systems interacted with their galactic environment. The possibility that the star's behavior was triggered by encounters with interstellar material or other stars motivated detailed studies of galactic dynamics and stellar kinematics. These galactic context studies revealed that KIC 8462852 occupied an interesting position in the galaxy, with a somewhat unusual velocity and trajectory compared to other stars of similar age and composition. While these characteristics didn't definitively explain the star's behavior, they provided additional constraints on possible explanations. The stellar evolution community found in KIC 8462852 a test case for understanding how stars and their planetary systems evolved over cosmic time. The star's apparent maturity combined with its unusual circumstellar activity challenged conventional ideas about how stellar systems developed and aged. Detailed modeling of stellar evolution showed that stars like KIC 8462852 should have long since settled into stable, quiet states with minimal circumstellar activity. The ongoing dynamics around the star suggested that some process was preventing this expected evolution, or had recently reactivated dormant activity. The planetary science community contributed expertise in understanding how debris disks formed and evolved, drawing on knowledge gained from studying the solar system's asteroid belt and Kuiper belt. These comparisons helped constrain models of dust production and orbital dynamics around KIC 8462852. The comparative planetology approach revealed that KIC 8462852's behavior was extreme even by the standards of known debris disk systems. The scale and complexity of the inferred circumstellar structures exceeded anything observed around other mature stars, reinforcing the star's status as a truly exceptional object. The space mission planning community found in KIC 8462852 a compelling target for future dedicated observations. Proposals were developed for space-based telescopes specifically designed to monitor anomalous stars with unprecedented precision and time coverage. The star had effectively defined requirements for a new class of astronomical missions. These mission concepts pushed the boundaries of what was technically feasible in space-based astronomy. The need for extremely stable, long-duration photometry drove innovations in spacecraft design, thermal control, and pointing systems. While no dedicated KIC 8462852 missions were approved, the technology development influenced other astronomical space missions. The ground-based astronomy community organized around KIC 8462852 in ways that established new models for coordinated observations. Networks of telescopes dedicated to monitoring specific targets became more common, inspired by the success of collaborative campaigns focused on the anomalous star. These observational networks demonstrated the power of distributed, coordinated observations for studying transient and variable phenomena. The organizational structures and communication protocols developed for KIC 8462852 monitoring became templates for other collaborative observational programs. The amateur astronomy community found in KIC 8462852 an opportunity to make meaningful contributions to professional research. The star's brightness made it accessible to modest telescopes, while its unpredictable behavior meant that continuous monitoring by dedicated amateurs could provide valuable scientific data. This participation of amateur astronomers in professional research created new pathways for citizen engagement with science. Educational programs and outreach initiatives used KIC 8462852 as an example of how interested individuals could contribute to actual scientific discoveries. The patent and intellectual property implications of KIC 8462852 research were minimal but interesting. The unusual analysis techniques and instrumentation developed specifically for studying the star led to some patent applications, though most research was conducted in academic settings with open publication of results. The open science movement embraced KIC 8462852 as a model for how major discoveries should be shared and investigated. The transparency and collaboration that characterized the research became an example of how science could be conducted in the public interest. The philosophy of science community found in KIC 8462852, a rich case study for understanding how scientific knowledge developed in the face of anomalous observations. The star's resistance to explanation raised fundamental questions about the nature of scientific progress and the role of unexplained phenomena in driving theoretical development. Thomas Kuhn's concepts of paradigm shifts and scientific revolutions were frequently invoked in discussions of KIC 8462852's significance. While the star didn't ultimately trigger a revolutionary change in astronomical understanding, it demonstrated how anomalous observations could challenge established frameworks and drive innovation. The sociology of science community studied how the astronomical community organized itself around the investigation of KIC 8462852. The collaborative networks, communication patterns, and decision-making processes that emerged provided insights into how modern science functioned in practice. These sociological studies revealed the importance of informal networks and personal relationships in facilitating scientific collaboration. While formal institutional structures provided important support, much of the actual research coordination occurred through informal channels that developed organically around shared interest in the star. The history of science community began documenting the KIC 8462852 investigation as a significant episode in 21st century astronomy. The detailed preservation of data, communications, and decision-making processes provided unprecedented documentation of how a major scientific investigation unfolded in real time. This historical documentation was valuable not only for understanding the specific case of KIC 8462852, but also for gaining insights into how science operated in the digital age. The investigation provided a detailed case study of how global scientific collaboration functioned in practice. The science communication community found in KIC 8462852 both opportunities and challenges for engaging public interest in astronomy. The star's mysterious behavior captured public imagination, but communicating the ongoing uncertainty and complexity of the investigation required sophisticated approaches to science outreach. Educational institutions at all levels incorporated KIC 8462852 into their curricula as an example of how science confronted the unknown. The star became a valuable teaching tool for illustrating scientific methodology, the importance of evidence-based reasoning, and the iterative nature of scientific understanding. Museums and science centers developed exhibits around KIC 8462852 that allowed visitors to explore the mystery interactively. These exhibits demonstrated how astronomical observations were conducted and analyzed, giving the public insight into the actual practice of scientific research. The planetarium community created shows specifically focused on KIC 8462852 and the search for answers to its mysterious behavior. These presentations combined stunning visualizations with current scientific understanding, providing immersive experiences that conveyed both the wonder and the rigor of astronomical research. The impact of KIC 8462852 on popular astronomy books and magazines was substantial. The star appeared in countless articles and became the subject of several dedicated books that explored its discovery, investigation, and broader implications for our understanding of the universe. Science journalism evolved substantially during the KIC 8462852 investigation period, with reporters developing greater sophistication in covering ongoing scientific mysteries rather than just reporting definitive discoveries. The star became a case study in how to communicate scientific uncertainty and process to general audiences. The documentary film industry found in KIC 8462852 a compelling subject that combined scientific mystery with human drama. Several documentaries explored the investigation from different perspectives, showing how real scientific research actually unfolded rather than presenting sanitized accounts of discoveries. The academic publishing industry adapted to the needs of KIC 8462852 researchers by developing faster review processes and more flexible publication formats. The importance of rapid communication for coordinating observations drove innovations in how scientific results were shared and validated. Preprint servers and online collaboration platforms became essential tools for KIC 8462852 research, allowing researchers to share results and coordinate activities much faster than traditional publication channels allowed. This acceleration of scientific communication became a model for other time-sensitive research areas. The conference and meeting industry organized numerous specialized symposiums and workshops focused on KIC 8462852 and related phenomena. These gatherings brought together diverse communities of researchers and established new traditions for organizing scientific meetings around specific challenging problems. The research funding landscape was influenced by the high-profile nature of KIC 8462852 investigations. Funding agencies found it easier to justify support for astronomy when they could point to specific, compelling mysteries that captured public attention and demonstrated the value of continued research. Private philanthropy also became involved in KIC 8462852 research, with wealthy individuals and foundations providing support for observations and analysis that might not have been funded through traditional government sources. This diversification of funding sources provided additional flexibility for pursuing innovative approaches. The technology transfer from KIC 8462852 research extended into numerous commercial applications. Data analysis techniques developed for studying stellar variability found uses in financial markets, industrial quality control, and medical diagnostics. The STAR had inadvertently catalyzed innovation across multiple sectors. The international relations implications of KIC 8462852 research were generally positive, with the investigation serving as an example of how global scientific cooperation could address complex challenges. The collaborative nature of the research demonstrated the value of maintaining open scientific communication across national boundaries. However, the investigation also revealed some tensions between open science ideals and national security concerns. Questions about whether anomalous astronomical observations might have strategic implications led to discussions about information sharing policies and the balance between transparency and security. The space policy community took note of KIC 8462852 as an example of how astronomical discoveries could capture public attention and potentially influence support for space exploration and research. The STAR became a talking point in debates about funding priorities for space science missions. The regulatory implications of KIC 8462852 research were minimal but noteworthy. The investigation raised questions about how governments should respond to potentially significant astronomical discoveries, particularly those that might have implications for national security or public safety. International scientific organizations used KIC 8462852 as a case study for developing protocols for sharing information about potentially significant discoveries. The STAR highlighted the need for clear guidelines about how the global scientific community should coordinate responses to unusual observations. The ethical implications of KIC 8462852 research centered mainly on questions of data sharing, credit attribution, and public communication. The high-profile nature of the investigation created pressures that didn't exist for typical astronomical research, requiring careful attention to maintaining scientific integrity. The question of how to handle potentially explosive discoveries like possible alien technology was addressed through the development of new guidelines for responsible communication of extraordinary claims. The KIC 8462852 experience informed these protocols, even though the STAR ultimately didn't require their implementation. Research ethics committees at universities found themselves dealing with novel questions raised by KIC 8462852 investigations. The collaborative, international nature of the research created complex issues around institutional oversight and responsibility that hadn't been encountered in traditional astronomical research. The environmental impact of KIC 8462852 research was negligible in direct terms, but significant in its influence on broader environmental awareness. The star's story emphasized humanity's connection to the cosmos and the importance of maintaining dark skies for astronomical observation. Light pollution reduction efforts received support from KIC 8462852 research as amateur astronomers involved in monitoring the star advocated for darker skies. The scientific value of citizen observations provided compelling arguments for protecting astronomical observing conditions. The energy consumption of the massive computational efforts required for KIC 8462852 analysis raised awareness about the environmental costs of data-intensive research. This led to discussions about more efficient algorithms and the environmental responsibility of the research community. The long-term preservation of KIC 8462852 data required ongoing energy consumption for digital storage and access systems. This highlighted broader questions about the environmental impact of maintaining scientific data archives and the trade-offs between preservation and sustainability. The climate change research community found parallels between KIC 8462852 investigations and their own work in analyzing complex, long-term datasets for subtle signals. The statistical and computational techniques developed for studying stellar variability had applications in climate data analysis. The insurance industry took note of KIC 8462852 as an example of how extremely rare events could nonetheless occur, influencing approaches to modeling and pricing rare but potentially catastrophic risks. The star became a case study in thinking about tail risks and black swan events. The artificial intelligence community found in KIC 8462852 data a valuable training ground for developing algorithms capable of recognizing subtle patterns in noisy, complex data sets. The star's light curves became benchmark problems for testing new machine learning approaches. Neural networks trained on KIC 8462852 data were adapted for use in other pattern recognition applications, from medical diagnosis to industrial monitoring. The star had inadvertently contributed to advances in artificial intelligence that extended far beyond astronomy. The quantum computing community explored whether quantum algorithms might offer advantages for analyzing the complex, high-dimensional datasets generated by KIC 8462852 observations. While practical applications remained limited, the star provided motivation for exploring quantum approaches to scientific computing. The cybersecurity implications of KIC 8462852 research emerged as massive datasets were shared across international networks. The investigation highlighted the need for secure, reliable systems for collaborative scientific data sharing and analysis. Blockchain technology was explored as a potential solution for maintaining the integrity and provenance of scientific data, with KIC 8462852 observations serving as a test case. While adoption remained limited, the investigation contributed to discussions about trust and verification in scientific data sharing. The social media impact of KIC 8462852 continued to evolve as the investigation progressed. Online communities formed around the star that brought together professional astronomers, amateur observers, and interested members of the public in unprecedented ways. These online communities demonstrated new models for science engagement that blurred traditional boundaries between researchers and the public. Citizen scientists made genuine contributions to data analysis and hypothesis development through social media platforms and collaborative websites. The misinformation challenges posed by social media discussions of KIC 8462852 required new approaches to science communication. researchers learned to engage directly with online communities to provide accurate information and counter conspiracy theories or misinterpretations. The psychological research community found in KIC 8462852 an interesting case study of how people responded to scientific uncertainty and mystery. The star's unexplained behavior triggered a range of responses from excitement to anxiety, providing insights into how the public processed ambiguous scientific information. Cognitive science researchers studied how scientists themselves dealt with contradictory or inexplicable data, using KIC 8462852 as a real-world example of scientific problem-solving under uncertainty. These studies contributed to understanding of how scientific thinking actually worked in practice. The anthropology community examined how different cultures and communities interpreted and responded to the mystery of KIC 8462852. The star became a lens for studying how scientific knowledge was constructed and communicated across different social groups. Religious and spiritual communities found in KIC 8462852 various meanings and implications, from evidence of divine mystery to confirmation of humanity's cosmic insignificance. The star sparked discussions about the relationship between science and spirituality that reflected broader cultural tensions. The conspiracy theory community embraced KIC 8462852 as evidence for various alternative explanations, ranging from government cover-ups to alien visitation. While these theories lacked scientific support, they demonstrated how scientific mysteries could be interpreted through very different worldview frameworks. The debunking and skeptical thinking communities found in KIC 8462852 an excellent case study for teaching critical evaluation of extraordinary claims. The star's investigation provided clear examples of how to distinguish between legitimate scientific uncertainty and unfounded speculation. The science fiction writing community drew extensively on KIC 8462852 for inspiration, using the real astronomical mystery as a foundation for exploring themes of contact with alien intelligence, cosmic engineering, and the limits of human understanding. Hard science fiction authors appreciated having a real astronomical mystery to build upon, while more speculative writers used the star as a starting point for exploring far-out possibilities. The star influenced both realistic and fantastical approaches to science fiction. The gaming industry incorporated elements inspired by KIC 8462852 into various video games and online experiences. The star's mystery provided compelling narrative material for games focused on exploration, puzzle solving, and scientific investigation. Educational games and simulations were developed that allowed players to experience the process of analyzing KIC 8462852 observations and developing hypotheses about its behavior. These games provided engaging ways to teach scientific methodology and astronomical concepts. The art and design communities found in KIC 8462852 inspiration for works that explored themes of cosmic mystery and scientific discovery. Visual artists created pieces that attempted to capture the essence of the star's enigmatic behavior and its impact on human understanding. Music composers wrote pieces inspired by the rhythms and patterns found in KIC 8462852's light curves, translating the star's temporal variations into auditory experiences. These artistic interpretations provided alternative ways of engaging with the scientific data. The fashion industry even found inspiration in KIC 8462852, with designers creating collections that incorporated motifs related to stars, light, and cosmic mystery. The star's cultural impact extended into unexpected domains of human creativity and expression. The tourism industry began developing astrotourism experiences related to KIC 8462852, offering people opportunities to observe the star through telescopes and learn about its mysterious behavior. These programs combined entertainment with education and helped support dark sky preservation efforts. Planetariums and observatories around the world reported increased visitor interest in programs related to KIC 846285 and astronomical mysteries more generally. The star had helped rekindle public enthusiasm for astronomy and space science. The amateur astronomy equipment market experienced growth, driven partly by interest in observing KIC 846285 and similar objects. Manufacturers developed new products specifically designed for precision photometry and variable star observation. The book publishing industry saw numerous titles related to KIC 846285, from technical monographs for specialists to popular accounts for general readers. The star generated enough interest to support a substantial literature across multiple genres and audiences. Academic publishers developed new models for rapid publication of results related to time-sensitive phenomena like KIC 846285 observations. The traditional publishing timeline was often too slow for coordinating observational campaigns and sharing urgent findings. The lecture circuit saw numerous presentations about KIC 846285 at universities, conferences, and public venues around the world. The star became one of the most popular topics for astronomical talks and presentations. Science festival organizers frequently featured KIC 846285 in their programs, using the star's mystery as a hook to engage audiences with broader themes about scientific discovery and the nature of the universe. The podcast industry produced numerous episodes focused on KIC 846285, reaching audiences that might not engage with traditional science communication channels. These audio programs allowed for in-depth exploration of the star's mystery in an accessible format. YouTube and other video platforms saw extensive content creation related to KIC 846285, ranging from serious scientific discussions to speculative conspiracy theories. The star became a popular topic for science communicators and content creators. The online education industry developed courses and modules focused on KIC 846285 as a case study in astronomical research methods and scientific thinking. These educational resources made the star's story accessible to learners around the world. Massive open online courses incorporating KIC 846285 content reached hundreds of thousands of learners globally, demonstrating the star's potential as an educational tool for engaging public interest in science and astronomy. The standardized testing industry began incorporating questions about KIC 846285 into science assessments, using the star's story to evaluate students' understanding of scientific methodology and astronomical concepts. Textbook publishers updated their astronomy and physics texts to include discussions of KIC 846285, ensuring that future generations of students would learn about this landmark case in astronomical research. The translation industry found significant demand for translating research papers and popular accounts of KIC 846285 into multiple languages, reflecting global interest in the star's mystery. International scientific conferences featured simultaneous translation services to accommodate global participation in discussions about KIC 846285, highlighting the truly international nature of the investigation. The archival and library science communities developed new approaches to preserving and organizing the vast amounts of data and documentation generated by KIC 846285 research. The star became a test case for managing complex, evolving scientific datasets. Digital humanities scholars began analyzing the social and communication patterns surrounding KIC 846285 research as a way of understanding how scientific knowledge was created and disseminated in the digital age. The legal community found few direct implications from KIC 8462852 research, but the STAR did inspire discussions about intellectual property rights in collaborative international research and the legal status of astronomical discoveries. Patent attorneys dealt with a small number of applications related to techniques and instruments developed specifically for KIC 8462852 observations, though most research remained in the public domain. The venture capital community showed some interest in technologies developed for KIC 8462852 research that had potential commercial applications, particularly in the areas of data analysis and precision optical systems. Startup companies were founded based on technologies originally developed for astronomical applications, but adapted for terrestrial uses in areas like environmental monitoring and industrial quality control. The career counseling industry began highlighting KIC 8462852 as an example of how diverse skills could contribute to scientific research, encouraging students to consider astronomy and related fields. Professional development programs for scientists used KIC 8462852 as a case study for teaching collaboration, communication, and project management skills essential for modern scientific research. The research administration community developed new protocols for managing large-scale, international collaborative projects based on lessons learned from KIC 8462852 investigations. Grant writing workshops began using successful KIC 8462852 research proposals as examples of how to present compelling cases for funding unusual or high-risk research projects. The research integrity community found relatively few issues with KIC 8462852 investigations, but the high-profile nature of the research led to increased attention to proper data sharing and credit attribution practices. Scientific misconduct investigators developed expertise in analyzing the complex, collaborative research structures that characterized KIC 8462852 studies, though no significant misconduct cases emerged from the investigation. The peer review training community used KIC 8462852 papers as examples of how to review research on novel phenomena that lacked clear precedents in the literature. Editorial training programs for scientific journals incorporated discussions of how to handle submissions about potentially groundbreaking discoveries, like those related to KIC 8462852. The scientific communication training industry developed specialized programs for researchers involved in high-profile investigations, like KIC 8462852, teaching skills in media relations and public communication. Crisis communication consultants worked with some institutions involved in KIC 8462852 research to prepare for potential scenarios involving extraordinary discoveries or public misunderstanding. The technology forecasting community found in KIC 8462852 an interesting case study of how unexpected discoveries could drive rapid technological development and innovation. Innovation management specialists studied how the KIC 8462852 investigation had catalyzed new approaches to collaborative research and data analysis that could be applied in other domains. The knowledge management industry developed new tools and approaches for organizing and accessing the vast distributed body of knowledge that accumulated around KIC 8462852. Information architecture specialists designed systems for making KIC 8462852 research data and results accessible to diverse communities of users with different technical backgrounds and needs. The user experience design community worked on interfaces that allowed both professional researchers and interested amateurs to interact effectively with complex astronomical datasets like those from KIC 8462852. Data visualization specialists developed new techniques for representing the complex, multidimensional information contained in KIC 8462852 observations and analysis results. The research collaboration platform industry created new tools specifically designed for the kind of global real-time coordination required for projects like KIC 8462852 monitoring campaigns. Version control and data management systems were enhanced to handle the unique challenges of collaborative astronomical research involving massive datasets and diverse analysis approaches. The cloud computing industry adapted their services to meet the computational needs of KIC 8462852 researchers, developing specialized tools for astronomical data processing and analysis. High-performance computing centers optimize their systems for the specific types of calculations required for modeling complex circumstellar dynamics, like those around KIC 8462852. The artificial intelligence industry found valuable training data in the KIC 8462852 datasets, using the star's light curves to develop and test new pattern recognition algorithms. Machine learning service providers developed specialized tools for astronomical time series analysis that were initially motivated by KIC 8462852 research, but found broader applications. The sensor and detector industry responded to demands from KIC 8462852 researchers for more sensitive, stable photometric systems capable of detecting subtle brightness variations. Optical systems manufacturers developed new products specifically designed for precision stellar photometry, often using requirements derived from KIC 8462852 observation needs. The precision timing industry found new applications in coordinating simultaneous observations of KIC 8462852 from multiple locations around the world. Atomic clock and time standard providers enhanced their services to meet the synchronization needs of distributed astronomical observation networks. In the end, KIC 8462852 had become far more than just an anomalous star. It had evolved into a cultural phenomenon, a technological catalyst, and a symbol of the enduring mysteries that still existed in our universe. The star continued its enigmatic dance 1,400 light-years away, largely indifferent to the enormous impact it had made on human society and scientific understanding. The investigation continued, driven by an ever-growing community of researchers, citizen scientists, and curious individuals who refused to accept that some mysteries might remain forever unsolved. New observations were planned, new analysis techniques were developed, and new theoretical frameworks were proposed, all in pursuit of finally understanding the star that had defied every scientific theory. Whether the ultimate explanation would prove mundane or extraordinary, KIC 8462852 had already achieved something remarkable. It had reminded humanity that the universe still held secrets waiting to be discovered. In an age when many felt that science had explained everything worth explaining, this single star stood as proof that mystery, wonder, and the possibility of revolutionary discovery remained alive in the cosmos. As you settle into sleep tonight, remember that 1,400 light-years away, KIC 8462852 continues its mysterious performance, dimming and brightening according to patterns that remain undeciphered. The star carries on its cosmic dance, patient and persistent, waiting for human ingenuity to finally unlock its secrets. In that ongoing mystery lies a profound reminder of how much we still have to learn about the infinite, surprising universe that surrounds us all.